Welcome back to a wet ECE 220. I'm sure you can tell by looking at the screen how rainy it is outside, but we know it's a little bit damp. But the lecture will just be as dry. No, it's not going to be dry. Oh, that's a... All right, let's move on. Lab 1 is starting today with the section E, and then we will continue with all of Group A this week. Make sure you bring in your pre-lab paper to work from or to use that, because I think you're checking your work as you work through steps in lab number 1. Homework number 4 is also due today, and if you need to brush up on your linear algebra or understand how you might be able to use that, refer to Appendix A in the textbook. Group B, or Section I in this class, your pre-lab for lab number 1 is due on Saturday, and we're trying to finish up Chapter 4 so that we can move into Chapter 5 probably next week. That's the plan, and that's now op-amps, or operational amplifiers. If we get there, I think the way that it's structured, exam number 2, I know we're not thinking about exam number 2. Exam number 1 is, did I have that on the screen? That is Thursday in 2 days, so please be ready to spend an hour of intense, focused, concentrated effort on solving all of these Ohm's laws, KCL, KVL, etc., chapters 1 through 3 material on exam number 1. Today what I want to do is combine and split sources, whatever that means. We'll try to become a little bit more comfortable with that, but before we do that, let's just convince ourselves that when we do these source transformations, all bets are off when we start doing power. We don't want to be thinking about the power being equivalent inside these conversions that we've performed. That's not going to happen. We will, in some of the examples, combine sources, meaning if we have 2 voltage sources in series, we can combine those into an equivalent single voltage source. And you could see that by applying KVL at, for example, node A, or between node A and B, at these 2 different representations of an equivalent source. Question? Oh, why does, I don't know why it says V. The valid question. That's what happens when you start doing this quickly. Vx didn't exist, but Vx could have been VAB, but then it wouldn't be right. So Vx was probably floating around in my head, but it's V1 minus V2 on the right-hand side, and on the left-hand side, the equivalent source when you combine 2 sources, voltage sources in series, you algebraically combine their voltages. And this is going to be useful if we end up with 2 Thevenin equivalents that are effectively in series. Oh, now we can collapse those, combine those to produce 1 Thevenin equivalent, because we know how to combine resistors in series. The dual of that is associated with current sources. We need to be able to combine current sources. And here what you might be thinking of is, if this is now A, can you combine or look at KCL at node A? And that needs to be true or equal in the 2 source representations. Performing KCL at A, node A, allows you to convince yourself that these 2 combinations of current sources are indeed equivalent. On the left, they're both headed in the same direction. You would expect the sum to be in the same direction. On the right, they're actually opposite to each other, and that means you have to algebraically combine their values. We'll go through an example where we simplify a circuit using source transformations. Then we'll look at another example where we do source transformations when there's a dependent source in the mix. And if that's the case, then we have to make sure that we retain the dependent variable that's somewhere in the circuit. We talked about source combining or combining sources. We can also split sources, meaning maybe to make your analysis easier, you might want to split a voltage source, and this will make more sense when we work through an example. Hopefully it's clear that what's on the left in this voltage source equivalent is consistent at the terminals as it is on the right. Similarly, with the current source, we can actually just say, well, what if we just put two sources in series and they're both producing I? We can split a current source into pieces. We'll do that with some examples and show how we can redraw a circuit using source splitting, where the source that we will be splitting will be a current source. Then we'll look at another example where we split a voltage source. And I know you don't want to go anywhere today other than this classroom. We're just stuck here. So we'll do this example as well. It may be noon, but that's okay when we get to this example. But this one now is trying to boil everything down to one Thevenin equivalent, and we're going to do that by combining and splitting as we go, as needed. That one we need to make sure we have our seat belts fastened and we're ready to go for working through that particular problem. First, though, let's remind ourselves of the fact that source transformations, if we're worried about how the power associated with those sources, they are not the same. To get us started, let's just make sure that we can remember or recall how to generate an equivalent source. On the right-hand circuit, I actually want it to be a Thevenin equivalent relative to the Norton source of 4 ohms in parallel with the 6 amp current source. I want to now do a source transformation. Where the equivalent source on the right we have to determine based on, and now we're doing it on the other side of what we did yesterday. A lot of the ones we did yesterday, our source was on the left of our circuit. Now our source that we want to convert is actually on the right of these terminals A, B. What's the blue horizontal resistor in our Thevenin equivalent on the right? What's its value? If we are now trying to change this into a Thevenin equivalent. How do we deal with the resistors? What's that R going to be? 4. It carries over, So that 4 that was in parallel with the current source is now the same value of R4 in the series connected resistor with this is now, and the polarity is going to be consistent with the direction of the current source. Our voltage polarity will be plus minus from top to bottom. And what's the value of that voltage source? If you virtually erased what was to the left of nodes A, B, what value of voltage would you need to have the same open circuit voltage on the right as you have on the in the left circuit if we've disconnected the 12 volt and 2 ohm network? Isn't it I times R? Or it's now 24 volts in the circuit on the right. Now what we want to do is demonstrate that the components of the source that we've now transformed, the 4 ohm resistor and the 6 amp current source, will be experiencing different powers than what we have over here in the right hand side with that 24 volt voltage source. How do we find V sub AB on the left? Here I say find it using node voltage analysis. What does that look like? We're just summing currents out of that, or algebraically summing currents out of node A. What's the current going to the left out of node A in terms of V sub AB and the other variables in the circuit? I gave myself a lot of room, a lot of space to write that. That's the current going to the left out of node A. V sub AB minus 12, that's the voltage dropped in that direction divided by 2. What's the voltage what's the current going down from node A through that 4 ohm resistor? That's Ohm's law. VAB over 4. And how do we account for that 6 amp source if we're writing KCL at node A? It's minus 6 out, isn't it? Or we now have minus 6 equaling 0. Now we can solve that for VAB. We have one equation in one unknown, the unknown being V sub AB. If we multiplied everything by 4, all terms by 4, we would have 2 VAB minus 24 plus VAB minus 24 equaling 0. That's just this multiplied by 4. And we now have 3 V sub AB equaling 48, or V sub AB is now equal to 16. What about over here on the right? Can you now find V sub AB? If we wanted to, maybe we don't need to. Maybe we just find that current I. It's one series mesh, one series loop. We'd have minus 24 plus 4I plus 2I. So we have minus 24 plus 4i plus 2i plus 12 equaling 0. Or 6i is equal to 12, or I is equal to 2. And with that collection of information, we should be able to find the powers associated with each element in these two different circuits, left and right. Let's do that. And we might actually need that current. What is that current? If V sub AB is 16, the voltage drop from right to left is 16 minus 12, or 4, divided by 2. So this is now 2 amps. And what's this current? 16 divided by 4, or 4 amps. It better be consistent with that 6 amp source coming in, and now we have a check. We could have written KCL. We now have 6N is equal to 2 plus 4 out. We're computing those so that we can now more quickly figure out what's the power. And now these are consumed or absorbed powers with our passive sign convention. What is the 12 volt source consuming? What's the equation? It's VI, where V is the voltage of the source and I is the current through the source. And what's the sign relationship relative to how the current is flowing and the voltage polarity is labeled using the passive sign convention? On the left, it's 12 I sub 2. It's the sign, SIGN, in front of that 12 times 2 using the passive sign convention. Isn't it positive? The power consumed by this is then plus 12 times I sub 1, which is 24 watts, where this was now what we calculated to be 2. What about the power consumed by the 2 ohm resistor? Ri squared, isn't it? Where I is 2. This is now 2 times I sub 1 squared. That's 2 times 4, or 8 watts, and the sign is consistent in terms of the passive sign convention. That resistor, the 2 ohm resistor, is consuming 8 watts. And if that 12 volt voltage source is consuming 24 watts, what are we doing to that 12 volt battery? We're charging it, aren't we? If it's now needing 24 watts, what about the 6 amp current source? What's the power consumed by it? VI. What's V on that current source? Is it anywhere? Do we have it? What's the voltage across that current source? Is that current source in parallel with anything? And do we know what that parallel element's voltage is? We found it, didn't we? We found it to be VAB. And the polarity is from negative to positive, is from bottom to top. So the voltage on that 6 amp current source we know, and using that VAB value, what's this sign in front of this formula, which is voltage times current? What's the sign in front of that using the passive sign convention? Here we're doing minus plus VAB. That is now entering the negative terminal before it goes through the element, that now passive sign convention says, oh, this now needs to be a negative relative to how we have defined the variables. And V sub AB, what was that? 16? So now we have minus 96 watts consumed by that 6 amp current source. Or it's in supplying or developing power. What about the 4 ohm resistor? That's Ri squared. We have the I through that. That's 4. This is now 4 times I sub 2 squared. So that's 4 times 16, or 64 watts. Does that seem to be consistent? Are we supplying the same amount of power that we're consuming? Yes, so our power's balanced. That's a good check. And here is the one that we want to pay attention to in terms of comparing this 6 amp current source. That was in our supply, or the source that we transformed. We want to compare that with this 24 volt source that we found the equivalent source for. Let's now do the same thing over here on the right. What's the power of the 12 volt source? Isn't it 12 times capital I and the passive sign convention? It's 24 watts. What about the 2 ohm resistor? And those are consistent between the two circuits because we didn't transform that part of the circuit to the left of terminals A and B. And that's what we said. We're okay if we don't worry about what's going on internal to the source that we've now transformed. But now, whoops, we don't have a 6 amp. We actually have a 24 volt source now. What's the power of it? Formula-wise, VI, where V is 24, I is, we calculated to be 2, and what's the sign on that formula? And it's minus because of the passive sign convention. I was 2. This is now minus 48 watts. And that we said we wanted to compare. So it's different in terms of power being supplied. What about the 4 ohm resistor? That's now 4 times capital I squared. What was I? 2? So now we've really messed things up relative to the sources. Those powers are not the same internal to those nodes A and B. But does the power balance? Yes, so we're okay there, but now what's the, if we were using the book's terminology and we said the power developed in the circuit, on the left, what's the power developed in the circuit? So the developed power is what they're meaning to be what is supplied by the elements in this circuit. These circuit elements are supplying watts. That one source is applying or developing 96 watts. In the book terminology, then, we would say, oh, that particular circuit, because of that 6 amp current source, the power developed in the circuit is now, we're going to report that as P of the 6 amp is now 96 watts. Or maybe I shouldn't say that because that's what we labeled for the minus 96. Let me just say the power developed or that's the power supplied by the circuit. What about over here? What's the power developed in the right-hand circuit? 48 watts. That's the power supplied, and those are not the same. So when we start doing source transformations, we can't be worrying about the power associated with those sources that we've now tried to transform. Here, the power developed is 48 watts, and that's the power supplied by the circuit. This was that cautionary warning that I had made yesterday. If we start trying to compute powers inside the sources that we've transformed, we're not going to get consistency. Question?
So, in the circuit above, because are we using ISO1, the 2 amps, for all of our equations for the right-hand circuit because that's the current related to outside force?
So I wouldn't. So the question was, what current are we using? What you can do is you can say anything outside of terminals A and B should be consistent. And it is. The current flowing in that 12-volt voltage source, 2 amps, in both cases. The same with that 2-ohm resistor. Internal to A and B, where we made the equivalence, don't be thinking that things are going to be consistent. That's the bottom line for this example. Now, let's move into using these source transformations to try to simplify what's between nodes A and B. Let's see if we can boil this down to a source in series with a resistor. Can we obtain a Thevenin equivalent for this mess? If we look at this for a little bit, do you see that this, what does that look like? What kind of a source? How are we labeling that? Norton or Thevenin? This is a Norton. What about this? What's that look like? Whoops, I didn't even give you the value, did I? What's the value here? Let's say this is now 30 volts. What does that source look like? It's a voltage source in series with a resistor. That's the Thevenin. But do you see how those are connected to each other? They're in parallel with each other. They share two common nodes. This Norton source and that Thevenin source are in parallel. we now have effectively, we're trying to get to this. That's our goal. We would like to boil it down to just a source in series with a resistor. Now we have a Thevenin and a Norton source, two of those in parallel. If we have things in parallel, how could we combine them? What kind of sources would we need? Wouldn't we need consistency? We would need either two Thevenins or two Nortons. Which ones go together in parallel? Nortons. We need Nortons. If they're in parallel, we need to convert the Thevenin into a Norton. Is that clear? We have two things that are in parallel. They're different, but they're in parallel. Let's convert one of them so that we can combine the two once we've converted one. So they're in parallel. Norton and Thevenin. Let's now make parallel sources. That means we need to convert that Thevenin source into a Norton source. Or it now was looking something like this, wasn't it? Where this was now 30 volts and this was 2 ohms. Let's say that we, just so that we're kind of all thinking the same, let's call that node X and this node Y. Now down here, this is Y and that's X. How do we convert that into a Norton? What does that look like for its equivalent between X and Y? What do we do with the resistor? We leave it with the same value. Now it's going to be in parallel with a current source. And which direction does that current source flow positively? Or where's the arrow pointed, up or down? It's going to be consistent with the polarity of our voltage source, where you have a current source going up, and what's its numerical value? V over R, which is 30 over 2. That's now 30 over 2, or that's now 15 amps. That now, between X and Y, do you see where we can now put that in here, back in our circuit? We replace that series voltage source resistor with a parallel Norton source between nodes X and Y. Or I now have the following. I have A, and I also have I didn't change anything here. That was a 5 and an 8. But now, between X and Y, I now have a 2 ohm and a 15 amp, and then that connects with B, where that particular resistor was 1.4, and this was our node X, and this was our node Y. Do you know what I want to do now? Now I want to combine these sources. That's what I talked about earlier in today's class. We want to be comfortable combining things. I have two current sources in parallel, and they're both going in the same direction. I can collapse those into one current source. I have two resistors that are in parallel. I know how to combine those. Definitely for Thursday's exam, I know how to combine two resistors in parallel. I now combine 8 and 2. Or 16 divided by 10, or 1.6. And if I combine the sources, what does it look like in value? It's just 5 plus 15. It's now 20. Now I've collapsed. I've combined those two resistors into one, two current sources into one. Now I just have a single source between my resistor on the left and my resistor on the right. So let me put those together. Now I have collapsed things down to where I now have 20 amps. And I have a 1.6, and here is now a 1.4, and there's B. There's A, and there's 2. What's this source? How do we describe that? Norton or Thevenin? Norton. But that source in that red blob is in series resistors on either side. And how could I make my source look more series-like instead of parallel? Now I simply need to convert that Norton into a Thevenin equivalent. Or now I can say, oh, I have a 2 there, and now what does my Thevenin equivalent look like? Maybe I should do it in blue so that you see what I'm... What do I do in the unlabeled elements? Can I label them? What's the resistor value? My R doesn't change in going from Norton to Thevenin or Thevenin to Norton, so this is now 1.6. What about my voltage polarity? Plus on the top or plus on the bottom? Needs to be consistent with the 20. And what's the value of that voltage source? And that voltage now is between those 2 points. This is now 20 times 1.6, or 32 volts. Now do you see what I want to do on the right? I can combine those in series, and in fact, that series combination, which is 3, is also in series with that 2. I can slide those resistors on either side of that voltage source and maintain consistencies at my terminals A and B. What's my net series resistance? 2 plus 3. I now have a resistor of 5 ohms. And what's my voltage? There's B. I didn't change anything in it. It's now 32 volts. And now if I said there's A, but do you see that that's equivalent to that? And here is what I was hoping to find. That was my goal, was to find this Thevenin equivalent of that other interconnected network that we began with, which had 2 sources in it, a Norton connected and a Thevenin. We flipped them around, made the Thevenin a Norton so that they were in parallel. We combined sources. Then we needed that combination to be made into a series source, so we Theveninized that, new word, and then we combined everything in series to end up with that equivalent circuit. And you haven't even fastened your seatbelts yet. That was the easy one. All right, let's go on. Let's do a source transformation with a dependent source. Pardon? So now what would we do with this circuit? What would we do with this circuit? Why are we doing this? And we may get into this tomorrow. Is tomorrow Wednesday? It's not the exam day, is it? So what we may want to do is we may want to connect something between A and B, and that something might be different. Somebody might want to connect up a 100 ohm resistor. Somebody else may want to say, well, I need to look what happens when I connect up a 200 ohm resistor. I need to look what happens when I have a 500. Are you kidding me? I have to analyze this circuit all those times? No. Find one equivalent. And now at terminals A and B, you don't have to mess with all of this garbage. No, I shouldn't have said that. This network, now you've simplified it down. Now do you see that you could put one resistor between A and B very conveniently and find out what's happening to the load? That's the purpose behind these equivalents. It's to do it once, and then you can say, oh, give me a resistor. Give me another resistor. Do you have a resistor? And you're analyzing all of these different cases, but you don't have to analyze that circuit every time. You're done with it. Now you just have to put in one resistor and do some simple KVL or Ohm's law. Yes? So now the power or developed or supplied the same, not internal to A and B, is it? But external to A and B, it's fine. That's what you're worried about. You want to now analyze what's happening external to AB. So you're taking this black box, and out pops this nice series voltage source with a resistor. And now you can put whatever you want on AB, and the terminal characteristics are going to be the same as to what they were earlier. But you don't have to go through all of that analysis to find what's happening at the terminals if what you're doing is simply changing what's connected to the terminals. So you wouldn't want to worry about power in this 5 ohm resistor or 32 volt source. You're just saying, I don't care what the power company's giving me this. I just need to know what's happening at the load between terminals A and B. So that now when I have 20 different resistors, I just have to analyze 20 simple circuits versus having to do the analysis 20 times with a current source and a voltage source, and they're all connected differently. You're avoiding that by doing this fun simplification. Let's do some more simplification. Let's now transform this circuit and make it look okay relative to the terminals that you might be hanging something across. But now we have a dependent source present, which means that we now have to preserve that dependent variable's location in our circuit. We can't collapse that away and say, whoops, what happened to I0? We can't get rid of it. Don't know what color I am. So now with this dependent source, we actually have to preserve we need to make sure and keep that there. We can't be messing with that branch because that is determining sources. That dependent source is dependent on that current in that branch. We can't collapse that away. We have to preserve that in this process. Do you see how we can maybe simplify this? What does this look like? Isn't that a series combination? And it's a voltage source in series with a resistor. Thevenin, Thevenin, Thevenin. Right? What's this one? That's another Thevenin. Together, what are they? How are they connected? Can we just combine these two immediately? How could we combine voltage sources if they're in series? Are these two in series? These red blobs? Those sources are in parallel, are they not? That's begging us to convert each of these into its Norton equivalent and combine the Nortons and then back out a Thevenin from that reduced combination. These Thevenins are in parallel with each other. That's begging us then to Nortonize them, convert them into a Norton equivalent. How would we do that for the left Thevenin source? What would that look like? Doesn't it look something like that? And we could, if you wanted to really keep track of the terminals, you could have those coming, or the nodes, they could go off that way or they could go left or right. But what do I put on these elements? How do I label them? What's the resistor value? 5. So I'm now converting those sources to Nortons. What's the dependent voltage source going to become? It's now a dependent current source, and what direction is the current flowing? Up or down? Up. And what's the value of that current source? V over R, where V is 5 I sub 0, R is 5. This is now 5 I sub 0 over 5. That's now a dependent current source of value I sub 0. What about the rightmost Thornton? Thevenin. Now it's going to become I'll do the hard part. What's the current source? Up or down? Up. What's its magnitude? 38.5 over 20. Did everybody bring a sack lunch? We're going to be here a while. We're about halfway through the material that I wanted to get through. Now these are in parallel. Are they not? We can combine them. Combine those, we now have a single Norton source. Now we can make that into a Thevenin, and where do we end up? We now have that 50 ohm resistor in series with a Thevenin. I don't know where we'll pick up, but we'll pick up somewhere on Wednesday, which is tomorrow.